In this video, we're going to take a look at Unit 7, Lesson 9 practice problems. So this first one says that Jada cut out a rectangular piece of paper that measures 5 inches by 4 inches. So let me just get a picture of that drawn. So 5 inches by 4 inches. And Han cuts out a piece of paper, cuts out a paper sector of a circle with a radius of 5 inches. Okay, so Hans is going to be like a sector here. And I'm not exactly sure how much it's going to be, but I'm just going to draw just a random one. And this radius is 5 inches. And Han calculates the arc length. Okay, so this arc right here to be 2 pi. Whose paper is larger? Show your reasoning. Okay, so we're trying to figure out whose paper is bigger. So maybe we're looking at the area of each piece of paper. So we know that the area here is just going to be 4 times 5, which is 20 inches squared here. So that's the size of Jada's paper. So then we'd want to figure out for Han's paper what the area of that is. And we only have the arc length and then we've got the radius. So remember, arc length is part of the circumference. So if we took a look at what the total circumference is, okay, because circumference uses the radius. So this is going to be 2 times pi times 5. So our total circumference is 10 pi. And we've got 2 pi. So the portion that we have, okay, so our portion is 2 pi over 10 pi, or 1/5. Okay, so we have 1/5 of the circle because 2 over 10 simplifies. So this is 1/5 of the circle. So then we could calculate the area because again, we have the radius. So the total area of the circle is going to be pi times the radius squared. So pi times 5 squared. So this will be 25 pi for the area. And then we have 1/5 of it. Okay, so we only have 1/5 of the area. So let's just divide this by 5. So the area of the sector that we have is going to be 1/5 of 25 pi, or 5 pi. And so we want to compare that to 20. So we would want the decimal version of this. So 5 times pi gives you that the area of this little sector here is approximately 15.7 inches squared. So that means that Jada's is going to be bigger. All right, number 2, a circle has a radius of 10 centimeters. Suppose an arc on the circle has a length of 8 pi centimeters. What is the measure of the central angle? So we want to figure out again the portion that we have. So let me just draw a random arc or sector because I just like to have a picture. So this is 10 centimeters for the radius. And then the arc of the circle is 8 pi. So let me move this down. So this arc right here is 8 pi centimeters. What's the central angle? So we're looking for this. So again, we know the total of all the central angles is 360. So we want to be figuring out what portion of this circle we have. So we know the radius and we have part of the circumference. So let's figure out the total circumference. And circumference is 2 times pi times the radius. So our total circumference here is going to be 20 pi. So what is the portion of the circle we have? Okay, so the portion that we have is 8 pi out of 20 pi. So comparing the part that we have to the whole thing. So part of the arc is 8 pi that we have compared to the total of 20 pi. So those pi's will cancel. And then 8 over 20, both divide by 4. So 8 divided by 4 is 2, and 20 divided by 4 is 5. So we have 2/5 of the total circle. Okay, so this is 2/5 of our circle. So then we'll want to use that, okay, and do 2/5 of the total degrees. So 2/5 of 360, and then you can just type that in your calculator, 2 divided by 5 times 360, and you will get 144 degrees. All right, number 3, a circle has a radius of 6 units. For each arc length, find the area of the sector that defines this arc length. Okay, so our circle, okay, so find for each arc length, so these are all arc lengths, find the area of a sector of this circle, which defines the arc. So these are all our portions of our arc length. So let's get the total circumference first. Okay, so the circumference on this circle, the total would be 2 times pi times 6. So our total circumference would be 12 pi. So then this will help us get our portion of the circle. And then we want to find the area of the sector. So the total area is going to be pi times the radius squared. So 36 pi. So these are our totals. So let's figure out the portion that we have so that we can figure out the portion of the area. So we have 4 pi compared to 12 pi, since this is the arc length. So this is going to give us that we have 4/12 or 1/3 of the circle. So then we want 1/3 of the total area of the circle to figure out our sector area. So 1/3 of 36 pi is 12 pi. All right, number 3 tells us that we have a circle with a radius of 6 units for each arc length. So all of these here are arc lengths. Find the area of the sector of this circle that defines this arc length. Okay, so we need to find, we have the arc lengths. Okay, so arc lengths are part of the total circumference. So let's take a look at the total circumference would be 2 times pi times the radius, which is 6. So our total circumference is 12 pi. Then we're looking for area of the sector. So the area of our whole circle is going to be pi times the radius squared. So pi times 6 squared. So the area is going to be 36 pi. So what we want to do is figure out what portion of the circle we have so we can do that to the area. So we have the arc lengths. So let's compare what arc length we have to the total arc length, which is the circumference. And that will give us what portion of the circle we have. So 4 pi over 12 pi, so those pi's will cancel. 4 over 12 simplifies to 1/3. So we have 1/3 of the whole circle. So then we want 1/3 of the area, and the area of your circle was 36 pi. So 1/3 of 36 pi is 12 pi. So 12 pi units squared would be the area of the sector associated with this arc. So then we'll do that again. So for this next one, it's 5 pi out of a total of 12 pi. So then the pi's will cancel, and 5 over 12 doesn't simplify. So we'll do 5/12 of the area this time. And so 5/12, so 36 divided by 12 is 3, times 5 is 15. So we have 15 pi units squared here. The next one we have for 10, okay, we've got 10 out of 12 pi. So now there's no pi to cancel because it's not 10 pi units, it's just 10 units, but 10 and 12 both divide by 2. So 10 divided by 2 is 5, and 12 divided by 2 is 6, and we still have that pi. And then we want to multiply this, so we have 5 over 6 pi is our portion of the circle. So then we'll multiply this by the area to figure out what portion of the area we have. So now you've got a pi that will cancel. So you'll multiply this, will be on top, really. Okay, so we've got this on top. When we multiply, so these pi's will cancel. 36 divided by 6 is 6. And 5 times 6 is 30. So we just get 30 units squared for that sector. And then we can look at doing it with just an L. So let's follow this same process. So we have L out of 12 pi. So that won't cancel. This is the portion of the circle that we have. Nothing simplifies. And then we'll multiply this by our area. Okay, so again, when we multiply, this will multiply onto the top. So the pi's will cancel. And 36 divided by 12 is 3. So the area of our sector will just be 3L, or 3 times the arc length. So if you take a look at this, 3 times the arc length. 4 pi times 3 was 12 pi. 5 pi times 3, 15 pi. 10 times 3, 30. So that was kind of the formula or the pattern that was happening in this problem. All right, number 4, select all the sectors which have an area of 3 pi square units. Okay, so we want sector area. Let me get a little bit more space here. So a sector with a radius of 6 units and a central angle of 30. So we've got a radius of 6 units gives us a total area of pi r squared. So 36 pi. And then a central angle of 30 degrees. So if I did 360 divided by 30, that fits in there 12 times. So I'm going to divide this by 12 because those are 12 equal pieces. Okay, 12 equal chunks is how many times 30 goes into 360. So 36 pi divided by 12 is 3 pi. So A has an area of 3 pi. So again, we see a radius of 36, or a radius of 6. So the area is going to be 36 pi. Well, if we have a central angle of 45 now, that can't be 3 pi because this one was 3 pi with a 30-degree central angle. So this one can't be. Also, 45 goes into 368 times. So we'd be dividing this by 8 if you wanted to finish it out, which is not going to be 3 pi. A sector with a radius of 3 units. Okay, so the radius is 3 units. That means the total area of the circle would be 9 pi. And then we have a 60-degree sector. So 60 goes into 360 6 times. So we could divide this by 6. You can also be doing the central angle divided by 360 this way and multiplying if you want to. Okay, so 60 over 360 is a fraction of 1/6 because both of those divide by 60. So 1/6 of 9 pi, which ends up being 9 pi divided by 6. So similar to what I'm doing. And 9 pi divided by 6 is not 3 pi. D, we again have a radius of 3 units. So the total area is going to be 9 pi. 120 degrees fits into a circle 3 times. Okay, so we'll divide this into 3 equal chunks, and 9 pi divided by 3 is 3 pi. And you can, again, do 120 over 360, gives you your portion of the circle. Let me get rid of this. Okay, gives you your portion of the circle. 120 over 360 is 1/3. And dividing by 3 and multiplying by 1/3 are the same thing. A sector with a radius of 3 units and a central angle of 180. So again, this is a radius of 3 units, and now they changed the central angle, so we know this one won't work because it worked in D. D was 3 pi, so we can't change the central angle and keep the radius the same to get that same area. All right, number 5, a circle has a radius of 4 units and a central angle measuring 45. What's the length of the arc defined by the central angle? So 45, again, is one that nicely goes into 360. So if I do 360 divided by 45, I'll find out it goes in there 8 times. So this means we have 8 congruent slices. So if we take the whole length of the arc, which is the circumference. So if I take the whole circumference, 2 times pi times the radius of 4. So if I take the entire circumference of 8 pi and I divide it into 8 equal slices, that's how big each arc is going to be. So in this case, 8 pi divided by 8 is just pi units for each one. And again, you can certainly do 45 divided by 360 times the circumference as well. 45 divided by 360 times 8 pi is going to give you back pi again, because this is going to be 1/8 if you simplify it. And 1/8 times 8 is 1. So you're just going to get back pi. So either way is fine. Number 6, Claire and Diego are discussing inscribing circles and quadrilaterals. Diego thinks that you can inscribe a circle in any quadrilateral since you can inscribe a circle in any triangle. Claire thinks it's not always possible because she does not think the angle bisectors are guaranteed to intersect at a single point. She claims she can draw a quadrilateral for which an inscribed circle can't be drawn. Do you agree with either of them? Explain your reasoning. So do we think a circle can be inscribed in any quadrilateral? And so to me, I'm saying no, I don't think that's possible. And so then I want to draw a picture where I can show that it wouldn't work. So draw any quadrilateral that you can't get an inscribed circle to hit all the sides. And so if we do this circle is not going to extend long enough to hit both of these sides at the same time. So this would be a counterexample that would prove that Claire's thinking is correct. Number 7, triangle ABC is shown together with the angle bisectors of each angle. Draw point D that's equidistant from sides AC. So let me get AC marked on here. So here's AC. So equidistant from AC and AB. So if it's equidistant from those sides, that means it's going to be on the angle bisector of that angle. So it's going to be on this line. In order to be the same distance from the green side, it's going to be on that angle bisector. And then we want the point that we draw to be closer to side B. Side BC. So we want it to be closer to side BC. So let's put this point. So we know the point needs to be on this angle bisector, but I want it to be closer to the orange side. So right now it's the same distance from the green sides. So when it gets past the in-center here, then it's going to be closer to the orange. So here it's closer to the green than it is the orange. Here it's the same distance from all three. Here it's closer to orange. Still the same distance from the green, but closer to the orange. Now if it was here, right now it's not equidistant from the green ones because it's off the angle bisector. So it needs to be on the angle bisector on the orange side of the in-center. So anywhere in here. All right, then number 8, Priya and Mai are trying to prove that if two chords are congruent, they are equidistant from the center of the circle. Priya draws this picture. Then Mai adds in the perpendicular segment from the center to each chord. Priya says, I think we should try to use triangles because that's how we proved things before. Mai says, I think you're right, but how? Should we draw in some radii, help them complete the proof? Okay, so let's draw in a couple radii here. And then remember, we are trying to help them prove that these two segments, these distances are equal. Okay, so we're trying to ultimately prove that this side is equal to this side. So if we drew in those radii, right? So we know that all of these are equal. And I'm just going to kind of white out the rest of this space so that I can write over it. So we don't need this. This is in your book. I'm just going to write my proof here now. All right, so we know that segments AO, BO, so AO, BO, CO, and DO are congruent because they are all radii of the same circle. Okay, so we know that. Let me make this a little bit smaller. All right, so we know that all of those are equal to each other. Okay, so then we also know that AB and DC are congruent. Okay, so segments AB and CD are congruent because it was given to us. So then we know that triangles AOB and COD are congruent by side, side, side. So we see that we have these, let me get rid of this segment in here, but we see that those orange segments are congruent. And then now we also proved, well, we were given that these were congruent. So now we see all three sides are congruent in those triangles. So then the perpendicular segments here are altitudes. Okay, so those distances that they did, and let me give it a letter so that we can talk about it a little bit easier. So let me just add in M and N. Remembering that that center point is O, it's kind of covered up in mine. All right, so then we can say then, MO and NO are altitudes of the triangle since they're perpendicular. So they are the heights of the triangle because of that 90-degree angle. So since the triangles are congruent, they have the same height. So then those two segments must be equal.